In this video, we are going to learn the examples of sequence spaces. Now, before we get into the actual examples, let us quickly recall what we have done earlier. So, in the earlier examples, we have seen the matrix on R, then we have seen various matrix in fact on R2, then we have in fact seen the matrix even on Rn. Now, in Rn, what we have seen is any element has got finitely many coordinates, say x1, x2, xn. Let us ask a question, what about an element having infinitely many coordinates, something like this? Now, this element will belong, definitely it will not belong to any Rn for any n natural number. Then we say that it is belonging to an infinite Cartesian product of R, that is R omega. We denote it by R omega. So, we can observe that x is in R omega if and only if it is a function from set of naturals to R, because we are writing x1, x2, x3 dot 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 xn again dot dot dot, that means all these are the real numbers and they are infinitely many, whereas they are countably many if you observed. So, it is a function from naturals to R, but we already have seen such a set. Such a set we say it as set of all real sequences. So, real sequences, in fact if I collect all set of all real sequences, then that set we want to talk about now. We would like to in fact see whether we can define any norm and then accordingly a metric on such sets. So, going ahead, again let me recall that norm 1 we have defined on Rn as follows. It is simply component wise the addition of the absolute values of each of the component, that is mod x1 plus mod x2 plus so on up to mod xn. We can certainly try to have a similar norm on R omega, that is norm x1 we can define it as mod x1 plus mod x2 plus mod x3, but now we do not want to stop because there are infinitely many terms. So, it is summation or rather series n equal to 1 to infinity of mod xn. Now, there is a question, because if you look at the right hand side, it is an infinite series and we all know that it may or may not converge. So, there is a question that RHS it may not converge, and so there is a problem in well definedness of such a norm on the sequence spaces, that is set of all the real sequences. Then what to do? A solution could be, let us restrict our set of all real sequences. Instead of that, we will restrict to those sequences for which the corresponding series is convergent. That is the obvious solution that one can think of. So, what we do is look at L1, a sequence xn in R such that the series mod xn n equal to 1 to infinity is convergent. Now, on this L1, if I define a norm like this, then it certainly is well defined. In fact, we would like to prove that it is a norm on L1. To go for that, let us look at the first property. Let us take any x which is xn, a sequence in L1. Then what we know is this series is convergent. We also know that mod of xn for each n is non-negative. So, each term in the series is non-negative. Hence, I would like to say that the limit of the series must be non-negative. Note that for arguing precisely, what I need to take help of is the corresponding sequence Sn. We need to consider the partial sum Sn as mod x1 plus mod x2 plus and so on mod xn, and then I have to say that this partial sum, this each term Sn is non-negative and Sn is convergent because my series is convergent, and hence since each term of Sn is non-negative, the limit of Sn must be non-negative, but limit of Sn is precisely we denote it by the summation n equal to 1 to infinity of mod xn. So, it has to be non-negative. So, this is the first property which is easy to deal with. On similar lines, I would like to deal with the second property, that is if I have norm of some sequence x 0, that is series summation mod xn is 0 for some x. I want to prove then that each mod xn is 0, that is each xn is 0. In other words, I am going to get it as x equal to 0. Now, let me take Sn, the nth partial sum for mod xn. Now, Sn is monotonic increasing, that can be observed because each mod xn is non-negative. So, it is monotonic increasing and it is convergent. So, it has to converge to its supremum. That means, but whereas I already know that it converges to 0 because of this, I already know Sn converges to 0. That means, I must have Sn less or equal to 0 for each n. It means that summation k equal to 1 to n mod xk has to be equal to 0. Actually, it is less or equal to 0, but then it cannot be less than 0, that means it must be 0. So, this is addition of n non-negative terms is 0, that means each one of them must be 0, hence this gives me mod xn 0, that tells me xn must be 0 and hence I get x to be equal to 0. So, what one has to observe is, in arguing that it is a norm, we have to always take help of the partial sums, sequence of partial sums. So, on similar lines we can prove the remaining results, I mean remaining properties, and hence this is definitely a norm on L1. So, before we go for some more examples, let us have a question. So, let us take x equal to r omega, and for xn and yn, let me define a metric dxy as limit n tend to infinity of mod xn minus yn. Question is this a metric on x? Let us pause the video for a minute, you work it out and then let us discuss the answer. I am sure you must have answered no, and which is certainly a correct answer, and the reasoning is definiteness, that is the property that whenever dxy is 0 we must have x is equal to y, that is going to fail, because we may have two different sequences which are having same limit, and hence mod xn minus yn limit n tend to infinity may become 0, although xn and yn may not be same for each n. That means, by the way, if you observe carefully, the other three properties may get satisfied, we have to confirm that as well, but anyway the metric, it can never be a metric on capital X, right. So, now let us try to work out some more norms which we already had on Rn, we would like to extend or rather see whether we can have similar norms on R omega. So, let us look at norm 2 on Rn, that is we have defined norm 2 as square root of x1 square plus x2 square so on up to xn square. On similar lines, if I try to define on R omega, then it is going to be the series, that is square root of the series xn square. Now, again it is the same question that can arise, that is does the RHS convergent? It may not be a convergent series, and hence we again have to restrict our space to L2, that is all those sequences for which mod xn square, series mod xn square is convergent. Now, on this certainly this norm is well defined, I am taking a positive square root of the convergent series that we have. Now, we are not entering into the proof of this defines a norm, why we will see soon. So, let me move ahead to the third metric that we had on Rn, that is norm infinity we had defined, it is the maximum of ideally mod x1, mod x2 and mod xn. Now, on same lines obviously I would like to extend it to R omega, that is the maximum of mod xk, k belongs to n. Again there is a problem that right hand side, the maximum of mod xk may not exist. So, what to do? We again have to restrict ourselves to a proper subset. Now, here now the set is I want maximum to exist, or rather I may want to replace maximum by something similar for infinitely many numbers, that is the supremum, and hence we would like to take my set L infinity as all those sequences which are bounded, because once I take it bounded, this set becomes bounded and hence its supremum instead of maximum will exist, and hence we would like to define norm as supremum of mod xn. This becomes a well defined norm, and it can also be proved that it satisfies all the properties of norm. Now, we want to in fact make a more general statement, that is, I want to define LP space for p between 1 and infinity. We have seen one example, that is L2. Now, we would like to in fact make a general statement that take any p between 1 and infinity and define LP as all those sequences for which summation mod xn raised to p is convergent series, and then accordingly I can define norm p like this. Now, it is a challenging work to prove that this defines a norm. It requires some more machinery, because the first and the second property can be proved. For triangle inequality you need some more machinery, in fact, that is, some more inequalities you will require for proving that it defines a norm. So, let me quickly go through those inequalities, although I am not going to prove it, but those proofs are very much available in the notes that are being provided along with this video. So, let us quickly go for the inequalities. The first one is Young's inequality. What it says is, for any p greater than 1 and any q which satisfies this condition, if a and b are non-negative, then they satisfy some inequality like this: AB, the product, is always less or equal to a raised to p by p plus b raised to q by q, where the equality is going to hold if and only if a raised to p is equal to b raised to q. Using this, we can prove Holder's inequality, that is as follows: summation mod xi yi is less or equal to summation mod xi raised to p raised to 1 by p and summation mod yi raised to q raised to 1 by q. If you observe carefully, this is norm x in p and this is norm y q norm, right. This is what we are trying to say. Then third is Cauchy-Schwarz, which is simply coming from Holder's inequality. If I take p and q to be equal to 2, then I get Cauchy-Schwarz inequality, which we already have seen for inner product spaces. Then there are inequalities for in terms of series, in fact. These are the inequalities which are the extension of Holder's inequality, in fact, and there is a fifth, that is Minkowski's inequality, which is extension of Cauchy-Schwarz, in fact. These are the inequalities which we can use for proving that norm p is a norm on the LP spaces. Thank you.